In the current situation, as you must have seen, that there is no trust in transaction. Though we have number of processes in the system, there's a need for consensus for establishing the evidence of the ownership of information, which should be irrefutable, irrevocable, and it should be absolute. As far as the security in transaction goes, all digital content is man-made, and all domains that carry the information also is man-made. So the point here is the challenge that we need to really make it is how the data is accountable, irrefutable, and consented. If we are really looking at the approach of enabling evidence of true value for all stakeholders, there has to be a physical and digital content connect, which unfortunately is the missing point in traceable rights of information ownership. Just let me put the points in perspective. All of us here worldwide, are we sure where from the information is received by us? Part 2, what do we mean, or how do we mean to ascertain the veracity of a digital information? What means do you have? And if it has to be authentic response in case of a fraud, what is the time that it takes to realize that the information is fraudulent? Can we trust the transactions? Can we establish a bona fide identity on spot? If there is a product in FMCG, any product packaging, can we do that on spot, saying that it belongs to a particular owner who claims to be the manufacturer? Can the document that's been issued by anybody, can it be done on spot? Surprisingly, answer to majority of the questions are no. If it is yes, as no to be considered, there is a fundamental anomaly in the data security of all use, all types. So whatever we are getting using multiple analytics, we are still not conclusive about the data that is coming to you as to who it belongs to. Here is a process. What we have said is a hypothesis. We are saying there has to be absolute owner for the information, who is a creator of the content. There can be intermediaries who do the controller, and they get the consent from the creator, and there could be a number of transactors that go into. In technical parlance, it's been said is fiduciaries who control. But does this fiduciary have a live consent from every time a data is transacted from a creator? I don't think. If it is the matter, it should be understood. Our understanding is all the digital data in the world today have null value unless they have a physical layer connect. It's a very serious matter. What happens if the digital data is eroded? Because it can be morphed, it can be changed, it can be modified, it can be destroyed. That's the cycle of a data. So we are looking at a very new method of making this process, which is already patented in India as conclusive proof of ownerships of information. So it contains, it says, typical document, a package. It goes into printing. We use multiple techniques of nano tagging, nanoparticles, security inks, barcodes, the printing portion of it. And then that is linked to the conventional transactional processes, wherein the physical connect is always linked. Validation approval is a must. And then it comes with authentication. And the digital world can always use to connect to this through any of the technologies that's available today, without which the part here, what we said as consent grants for information owners, real information owners, cannot be established otherwise. So if you look at the scenario today, we are using multiple techniques. Okay, there are AIs, MLs, blockchains, whatnot. But the data created, something like 2.5 trillion, 20 trillion bytes every day. Now we are getting into zettabyte markets. It's growing multifold. and it's expected that somewhere around 25, 200 plus zettabyte of data will be in cloud storage around the globe. Question is, how are we sure the growing digital content is genuine? How much of it is genuine? And how can it be established as genuine? This is a very important issue for every common person on this planet Earth. Just to understand little bit more, in reality, this is my understanding, our research work, it says all the digital data is really null, though it has been said in a big way, saying that the digital data is authenticated and else. I don't think there is any process or any methods that can give the rapid decision value of a physical layer as a connect. The world is growing, as I said earlier, this information which is available to all the people, but there is no conclusive proof of data or information ownership. There is no process available which is conclusive. This word has to be understood. So here we have a simple model where we said the transactional guarantees, which is non-existent practice globally, though it has been described as transactions controlled by the blockchains. You get the connectivity of two blocks, last two blocks, but it never connects to a creator who is the owner. Invariably, the images or the content created in a blockchain is digital. It never has a connection to a creator who creates a value. How do I explain this? Okay, I am a human being. Unless I create a content of my own and allow somebody else to transact it, and I give consent for the transaction, the entire transaction process itself is flawed. So it's a must that we have consents of absolute owners for every bit of information that is connected with the physical layer to get the transactional guarantees. And this is non-existent and it's applied in different ways. So we call it as bridging the gap between digital and physical. We have already known that, okay, there are a number of systems that works on, there's a connectivity processes, but yet we don't have the real-time value of the transaction. Here, thanks to Dr. Rajan, we have tried to apply a certain advanced encryption program. This is something very different, and I don't want to get into the technicalities. I would rather come into the business process of how it drives. This is known as visual cryptography, attempted and tried out. We are trying to suggest that yes, this encryption can be deployed in all the content which is physical in nature, and it will give one single key to the physical owner. It's a constant which can be connected to a number of variables, which gets into the authentication of information that comes to. It can carry any information like timestamps, origin, validation, so on and so forth. The absolute ownership, it should be having a referential integrity, is exactly we are looking for auditable handshakes. And it has to be on spot. I don't think anybody in the world can today claim that the information that is presented to you is genuine or real, or you know the source from where it's originating at that particular point. And this subject takes us to what we have coined it as right to product information. This is accountable information rights adjudication. And there's no model. This is a model we are trying to bring in called as trusted information governance. And under this, the origin discoveries are based on physical parameter validation that are natural and immutable. Thereby, the evidential value does not diminish compared to digital parameters. This is a very unique proposition where we are saying that every data, every bit of data which belongs to somebody has to be approved by that entity, without which even the intermediaries who are authorized to do will not be able to suffice the value of the content that is to be ascertained as genuine. So, what is the value proposition? Accountable information ownership, which is non-existent today, is a concept of authenticity of transaction, and without this, any kind of digital value in the market today, no matter how much you say it is safe, is does not have any value. It may be a big statement, but then it's reality. So if they are really we are believers in technologies, the proposed method will definitely augment information value chain robustness, benefiting the information transaction process and is protagonist in disseminating the authentic and accountable information. We've been hearing in the markets, yes, there are plenty of fake news. Okay, billions of dollars goes into making this data transmitted across. How do I know that it belongs to a creator of that information is somebody at that particular point of time? I don't think we have any such model asset in the market. Here is where we have said that yes, the data ownership and the connected constituents have to come quickly and on spot. So coming speciality on the opportunity landscapes, what we look at, we started in somewhere around 2019. The pandemic really caused us the losses and delays globally. And our application perspective, we said, yes, it can apply to sourcing, manufacturing, and any supply chain logistics connected entity. What we term it as the loss prevention programs, revenue loss prevention programs. It comes in the classification of anti-counterfeiting, fakes, duplicates, name anything. That's the first level of entry for establishing the ownership of the information. And it's known as digifix, digital and physical, right? It's a diversified subject, applies to anything and everything where we are talking about. And to bring, track, trace, verify, and be sure on spot is IP-driven solution, and it's essential for any kind of product that comes into market. Visualize the situation. You are buying a bottle of water. Do you know that the manufacturer owns the responsibility of giving a quality product? What are the means do you have today? None. You rely upon the brand value, though there are a number of processes it goes into it, but there is no guarantee. Can there be a system which can give guarantee? Is exactly what we are trying to say, that the owner has to commit by some kind of a reading mechanism that we have developed now. It is an untapped market for anything and everything. To bring it into perspective, we looked at what if the insurance document, a policy, premium, and claim settlements. How do we know that the document submitted is genuine? And it should happen on spot. So here the algorithms that we use, the features that we use will immediately are connected to the owner whose consent is a very valuable input at that point of time. Just let me explain this one point. A global transport document, control document, it's a passport of identity of person to go in Hague conventions. How does the immigration know that who created that passport? We all know that, yes, it's created by passport offices. But is there a possibility of knowing who was the person who is authorized to create that particular passport or the visa, and who exactly allowed that person to enter into a nation? I don't think we have any process that though they may know discreetly in the covert operations, they may know, but then we do not know whether it's in a common man's domain to deny an entry, which is a genuine reason. Apply that simply to banking and fintech areas, the KYCs. We know what kind of scams and frauds happen. Yet, there is no process which tells you a person who has an account or transacted an account can be linked to the people connected with the transaction. And that should happen on spot. I'm repeating this word on spot because the approach of ours is to establish on spot the reality and the connectivity to the original information owner, without which whatever else is said is circumstantial, it's evidential matter. In this case, we have developed certain systems, certain designs which have to be uploaded. It can be in cloud, it can be in client-specific, premise-specific ownerships, and this is encrypted image information controlled by biometrics of an individual who is authorized to issue or share a document or information. A classic issue is the judiciary. A document produced in front of a judge by an advocate or an attorney, how does the judge know that the document is genuine? I'm very sure all of you will agree to this fact that yes, there is no process today which can give you instant guarantee of a document or a information given to the judge can be adjudicated as clean. That's a time consuming process. So we said if it can be applied to anything and everything that goes into it's a perpetual subject. It comes into the packaging, labels, tickets, coupons, name it. We are now trying to do it for establishing the dairy products in India, which can be measured by a consumer on spot, and it links to the absolute owner of a particular product and the units connected with it, when, what, how, where it is produced. It can apply to anything else. Okay, like said leather, it carries affluents, it carries chemicals not approved in several countries. How does somebody know when it lands into a country that yes, it's not processed with some kind of a insecticide or others, which is not permitted? It can happen to fertilizers. It can happen to anything else. Just now I was hearing about the food, about the farming, the supplies, the pesticide which goes into farming. How do they know that pesticide itself is genuine? And it should be known on spot again. So applications are plenty. Then we come into identity. It's a very huge subject. How do I establish my bona fide identity to anybody in the world? I'm a universal citizen. This has been dogging us for a long time. Then you said a document which is given, which can be measured, and it has a connectivity of an issuer. Seldom there is some subjects like this available. Though there are processes which says that yes, we can verify, we can vet it, we can attest it. But do we know that the attester is attested by somebody? I'm very sure there's none. Right? So it applies to any of the subjects. What is shown here, identity tools, is what we build as a software processes, and it goes into coming to automotive. Okay, we have developed a low application which will be able to establish the identity of a vehicle on a mobile platform. Any of the GPS in the world today can give you the density of traffic, but cannot give type of vehicle on that surface. I think I'm right what I'm saying. Now, if you have to find out there is a congestion, how do you know what type of vehicle in a particular stretch of a road? There is no means today. We know the density, yes, it is crowded. How do we measure? So we have built a small tracking unit which can be applied to all vehicles, and it carries nano materials, okay, to establish the ownership, the typical identity of the vehicle, which always talks to and tells. Part one is it identifies a particular vehicle using nanomaterial, which has a temperature of something like 1200 degrees. That's a protection part of the vehicle, and this is linked to a digital communication device which is always on mode, and it talks to the mobile platform or a roadside reader. It tells you instantly if some vehicle is wrongly parked but not permitted to enter, if it's in opposite direction, whichever way. This is something, a practical approach, which we call it as is also patented solution known as Mavises. Okay. Now this system can get into anything. Okay. Automotive, authentic automotive information, concealed consignments, containers, cartons, identification of special spare parts when it's applied with. To do this application of this particular nanomaterial, we built our own machine. We build our own machine. Okay. These particles of nickel has a capacity of withstanding up to 1002 degrees centigrade, and it's impossible to reconstruct since each particle of say 2 to 5 micron carries 7-character variable digit. It's once applied, it cannot be destructed, and it will not be visible to naked eye, and you require eyepiece to see. So it gets into FMCG, bulk packaging, dairy and its value. The encode system is a system for spraying and applying for readability of the particular particle that's embedded. There are different variants, silicons, metals. We have tried to apply this on the packaging to identify the packaging material itself is genuine. So we build end-to-end composite and integrated system comprising of software, hardware, machines, and service. Now, before I close this, I would like to bring it to the point of address here. This forum, I appreciate and thanks a lot to Dr. Rajan, who has been my mentor, who has been tutoring me on how to look at the world, the way it has to function. I may be little different from what other people speak about. It's a fundamental information right protection, which has never been spoken as on date. There are different theories, different mathematical models, but then as a common citizen, do I get the absolute guarantee of what I am receiving is never represented. This is what we are trying to attempt, and we are trying to bring it into reality sector, the property documents, the transport documents, name it, name anything else. Now, if it is taken as a business process, as I said, I'm a technician, not as a scientist, but it's a hands-on applications of what we are trying to do. This can be an order of the day where right to product information is a fundamental right to know for any transaction that gets into it and it's on spot. If this can be brought into different nations, and it can create definitely a sense of trust in governance, mutual trust. This will minimize all kinds of activities that goes on which are otherwise not accepted can be minimized. The litigations get reduced, more particularly the privacy laws. No one knows who is stealing your information or who is using your information. By virtue of this process, unless I give consent, okay, my information cannot be known by anybody. This is the point of address for technology. And the secure information, Dr. Rajan has been very kind in educating us and taking this to the next level where we are trying to bring it onto various application layers to documents, metals, and anything else. Thanks a lot. This can help any administration which is looking for protecting their information rights. It's a new protocol, new method that we believe will come into the world market. It can be far better or closer to GDPRs, what is being now proposed in European Union, and it's been done partly in US. I think the Asian soil can take this forward and establish their bona fide identity establishment in a very new method, which is not available as on today. Thanks a lot. Thanks a lot for time. Thanks everybody for listening to me.
Thank you, sir. Good morning, and thank you so much. And thanks to World Innovation and Tech Expo Investment Summit organizers and the team. In particular, thanks to Emmanuel Achu and and also Dr. Rajan E.G. Both of them, I like to thank them for a given opportunity to present in front of this good event audience. I do created a kind of bit of a few research in the emerging sensor networks, the world problems. But since of large nature of the sensors coming into new application like a driverless car and autopilot and space mission, in particular smart cities, the census network become a critical aspect to take autonomous decisions. That means the measurement has to be automated and then error-free things expected. There we use a new tool set called Convergent Duality. Of course, a old tool, but we are using it for a new problems. And it is something called abelian harmonic analysis. Olden days we do something called Fourier transforms, which is essentially related harmonic analysis, which is also called abelian because of it's a group nature into that. So I'd like to thank Professor S.S. Iyengar, is the co-author for this research, and Knight Foundation School of Computing and Information Sciences, Florida International University, USA. And I do work for bread and butter for a signal processing engineer in Mistral Solutions Private Limited in Bangalore. So in this, the red line which is clearly shown is a sensor fusions. The sensor fusion is a problem, potential problem, which you're trying to solve. Uh, because of the reasons which I told, it is emerging is a critical element in particular like smart cities and driverless car in it. But what we before going into that, we need to develop tools and method and apparatus to solve the sensor fusion problems. The one such a tool which is I selected is a Boltzmann machines, is a Boltzmann distribution. Another tools which is selected is a Brooks-Iyengar algorithm, which is essentially solve the similar problem. That's what I saw when I when I saw that. Then I got a good results quickly into that. First thing is I stitched these two things together and find what's the relation between Boltzmann machine and Brooks-Iyengar algorithm, which are very good interaction with Brooks-Iyengar, sorry, Iyengar itself in Bangalore. So that results we almost confirmed it's happening, and we could publish the results on that. What happened was in 1984, Boltzmann machine was used as a tool set to develop a posterior probability finding problem by Professor Hinton at Toronto University. This a result is going parallelly. The another interesting thing came from during 1996, Brooks-Iyengar algorithm was published, and it was trying to have a robust and yet precise computation of a parameter in sensor network. There are two things happening currently. One is in 1984 from Professor Hinton, Toronto University. Another is in 1996 from Brooks-Iyengar's results. These Brooks-Iyengar results more into the on sensor network or sensor problems, and this Hinton mode of like finding the network and then the probability distribution of the input. He was trying to train the network and then trying to find the probability distribution of incoming vectors. There are two different problems, but when I look at it, both of them appears to have a similar and the same nature of application. So I did use that. Issue here is where the sensor network might include a faulty. All the sensors are good, no problem, but the lots of pre-processing data always good. So we're trying to eliminate the faulty sensors. That's what which we call as a what is it called as a faulty sensors. Need to go away from decision making set of sensors, right? Then we use BA algorithm. I'll have a detailed presentation onto that. What happens is when the Boltzmann machines is more of a when the temperature high, the variance is very high, and the probability distribution is also with the quite amount of variance high into that when T is high. But when you keep reducing T close to lesser and lesser, it approaches zero, then become a Brooks-Iyengar algorithm. It's both are the same. BM will be deterministic. BA is already deterministic. So both them are handshaking. But at T is equal zero. Or converging close to zero, they are handshaking, but that proof needs to be, what do you call, like more or less, like almost I'm confident that need to be weighted out. That for Android in duality, the dual space of a sensor network is used as a space for a sensor classification and also to find the computability of measurement. There are two things. One is a sensor, and then using the sensor for measuring. So the measurement is, we can call it as a function on the sensors actually, right? And the sensors connected to the physical process. So the many measurement might have a same, physical process. We want to know what is a physical process which triggered so many, output strings actually. That's the way Android and duality play major role into the crux of this problem. A Fourier transform, one such a thing normally we use last 200 years. The dual element in the dual space can be element like a Fourier transform actually can be considered as one such a dual space of given network. This can one such example. But what happened is now this dual space of Android thing opens up a much more valuable, much easy to compute things also might emerge. That's what I think. Issue is not just sensor-based measurement. We have only assuming that the output of the sensors, whatever we measure, that's what we have with us. From that, we have to infer what could be the real data of the sense, physical state of the thing where sensor is attached. Sensor itself, adds the bias, itself adds the noise, everything before it's going to give the final one. Element in dual space. What happened here? On the when we say element in a dual space, is a critical one. To get that one, how do you do that? Kolmogorov complexity is to model the sensor measurement. How good that is. Entropy is very high or low. It's a periodic or non-periodic. That we can compute it by using Kolmogorov complexity. That problem is equivalent to the problem of computing the elements in the dual space. It is like I already told, like a Fourier transform, right? So the Fourier transform is element in the dual space of the sensor space, actually, G star actually. So the Turing machines, another concept which is computer science, which is borrow here, which is so given samples, GI from 1 to K, that is mapped to string SI via the Turing machine T. This is the one, like a Turing machine maps so many input samples to output sample Si. So yeah, one maps to output, right? So we have to find out the minimal P which does this work for us. P is a program which results in above given strings via during the machine. It's something like we bought S1, S2, Sn, then we want a 1P which result to that one. That's what the question. If we know that, then we know the Kolmogorov complexity of that. That's what it is about. Of course, it's proven that's very difficult to compute, sometimes doesn't exist also. But practically, we have to take some steps here. What is necessary and sufficient condition on a strings S1, S2, Sn are for existence of program P? I keep checking whether the internet is alive or not. Okay. So then if there exists a program P, then the same P computable or not. The question is, first of all, we know such a P exists, program exists or not. It is a 1P can be considered Fourier transform as example. Illustrate the thing, we can consider the Fourier transform is P can be like, find out the frequency like, 400 Hertz, 500 Hertz, like. If there exists a P, how to compute the method and apparatus? This is a problem which we do it. By solving this problem, we'll be solving the sensor fusion problem actually, with rationally. So the sensor network is just illustrated in this diagram, which has a green and red. Of course, green is suppose a lovable one, red is unwanted one, as the color says. Apart from this, we want to know what is the red, then and also accuracy of the measured value at range. How accurate our measurement done? That's what Brooks Iyengar algorithm touched, and they have been a result of 1996 to now almost 25 years, 26 years. It's still going on. A lot more research keep coming on to that. But what happens is, introduction to sensor fusion is a significant robust model-based inference actually. So instead of ad hoc one, we have a model-based inference. Then we need, kind of other things. For example, like a Brooks Iyengar algorithm is one such a model-based one. And then explanation, Boltzmann machine also gives one model-based one, but that's more of stochastic process-based. This Brooks Iyengar algorithm more of deterministic based. That's a key difference actually, vast difference. We use here is the mathematical concepts like Kolmogorov complexity, Pointryagin duality, and Turing machine in the context of sensor networks. In the computing program paradigm, all this use, but for us today's sensor network is one computing machine. Imagine one sensor is a computing machine. It's output so many strings for a given input, suppose. Then all these things in the storyline comes wherein the proposal here is, can we have a quantum sensing programs for a data observables? That's the kind of thing which will connect at the end of the few slides. I have these results onto that. Of course, this paper, paper is there in given to authorities. They can distribute it in the part of that. We can read fully, or you can request. I can send a copy also. So that's the reason I'm not cutting the details. If I have a necessity, I'll do stop and explain. So this is what the picture presently standing in front of us is essentially illustrates the Boltzmann network. It's a distribution network in which every node is connected to every other node. It's very complex. It's a solving is like still it's not there. But what presently is neural on the NVIDIA kind of things presently going more of restricted Boltzmann machine where all the nodes are not connected, only some of them kind of thing. So the assumption, but we consider the general one. In the our problem now here is some node might be biased also. It can have its own unintelligent act, so that might harm us. We consider that too also into our decision making process. Decision, I mean inference process, fusion. Since that fusion is a decision, that's called as inference in that one, right? So, of course, binary data can be, the sensor data can be much more, but we can consider it, for a simplicity understanding in this presentation, it's a binary vectors. So when we collected the data, from the sensors, the physical process that can be considered as a binary data. Now our approach is to model the binary data. What model we want? Distribution parameters, and then probability assignment binary vectors connected to the Boltzmann machine. The moment if we know that one, then we can connect this, what you call, edges and the probability, joint probabilities we can, compute it actually. This algorithms essentially, goes into the sensor fusion is a critical for automation of the deployed machines. Well, yeah, this is before going, getting B algorithm. There was a history into that called Byzantine general problem. It's a classical problem for distributed computing places where processors can took initiate and crack that Brooks-Iyengar algorithm. This is essentially a kind of a point-based measurement. Byzantine thing is there is a point measurement, only one measurement, and then every census and then take a thing. But instead that here in a B algorithm they have an interval measurement where the 0 to t seconds data is sensor is observed. Then that fusion is a more meaningful, more reliable than the Byzantine problem. That's what we use it now here. 215. Okay. Is I'm in the presentation session or I'm out of? Is it okay? Shall I continue? Okay. I'll assume that everything fine. I'll continue that. The sensor networks, it has two types. One is you can call it a deterministic left green one, right? So the stochastic network. Yeah, just trying to check the network is alive or not. So here what happens is a deterministic network, it can, and another is a stochastic. Under the stochastic we have Boltzmann distributions. In the deterministic we have Hopfield network and also multi-layer perceptron, and then we have Brooks-Iyengar algorithm. So in the idea here is how to connect this Boltzmann machine to Brooks-Iyengar algorithm either way or Hopfield. This is a kind of questions which you need to answer for us before we further proceed. That what is deterministic network is a category of sensor networks as MLP, which is told that it's a fully connected forward artificial neural network MLP, which is known that it is a backpropagation algorithm used for training that. Hopfield another networks, another side a recurrent neural network, but it has an energy function called Lyapunov functions. And then it is used for a combinatorial problem, sometimes series data model that. Now, can we reduce a Boltzmann machine to Hopfield network? That's exercise which we done. Then the reduction involves simplifying Boltzmann machine to a simple optimal net. What do we do actually? Why we want to reduce it? That's a question. What happened is when we reduce Boltzmann machine to Hopfield, then Hopfield network is more deterministic. We can start or get the results quickly instead of wasting 5 days and 4 days and so on and so forth. These are items since the fusion is happening. We cannot wait, on 10 millisecond or 3 millisecond to take a decisions, right? So we need a fast and quick algorithms to catch this thing. Otherwise, Boltzmann machines good amount of time to converge as such. Both models exhibited deterministic behavior at low temperature. When the T is equal 0, then both of them are good, like they agree on the mathematically. Model sensor networks includes the deterministic networks, and also it is stochastic is a Boltzmann thing, right? So it's a category of sensor networks. It is there. We can think of it's also like a nodes in the sense stochastic nature also, but where it is useful that we can discuss when it arises like. To get into the more details, we look at the what is present in general problems. And BGP is a distributed computing problems. It's a way algorithm using a measurement over the interval, convergence nodes, sensor fusion challenges computability of large scales. All the problem comes thousands and millions of nodes are there. Then the problem arises the computing one. That's we need a good amount of speedy algorithms to for a computing one actually. Bayesian networks are probabilistic graphical models. That's what the Boltzmann distribution, nodes, edges, and conditional dependencies, Boltzmann distribution and probability of state, keep sampling for joint distribution estimations, connection to the sensor networks and temperatures. Great. So then we have a Boltzmann machine and some network stretches. This is a kind of equations, the probability density functions, which is expressed in this form of temperatures and then energy level and the number of sensors. Suppose n number of sensors that is normalized with the bottom, and the top is only that particular node, in particular sensor for us. Boltzmann machine is a stochastic counterfeit of Hoppel network. That's what which I have been discussing it. It provides a probability distribution of the sensor node states. It gives the probability distribution, and the temperature parameters is and determine the probability. Either temperature and the distributions variation is very high. Intuitively, actually, it is true as well. Connection to the Boltzmann machine. Why do we need that one is it's a probabilistic modeling of pattern recognitions or a similarity. Boltzmann machine estimates joint probability of binary variables. Binary variable is a sensor here for us actually. Connection between Boltzmann machine weights and probability assignments. Boltzmann machine and digital twin. Of course, digital twin can be every sensor can be like digital. We can get a digital twin of sensors, which is nothing but the Boltzmann machines. Imagine so many of them are together in the network. That's what which we are talking about it like. Boltzmann machine and the sensor classification. Our aim here is to use these Boltzmann machines to classify the sensor data, one or the few sensor data actually. BM learns the joint probabilities, which I told about it, models the census data. The moment if we models the census data, then we have opportunity to classify or do predictions and so on so forth on that. Here, enhancing sensor classification techniques, Brooks-Sanger algorithm for this is like a early stage algorithm to pre-process the data whether a faulty sensor or non-faulty in a deterministic way. Then we go and model it rigorously. The past sensors we can say n minus r of them for get the Boltzmann machine for sensor classification. Then we construct the Pointryagin dual space for those n minus r, and then define a character function for a further process actually. So the first step is to remove the faulty one from the good. There we use the BI. BI is like a Brooks-Sanger algorithms. So that details are given in the paper. One can take in it how it is. Of course, measurements always can dominated with the error, sampling error, and so on and so forth. But still, we want to estimate the distribution parameters of the binary data. And that it has its own applications, which we have been discussing. One of them is classifications, and also find out its values. Measurement problems. So on the measurement problem between sensor networks and the measurement problems, a dual space represents the sensor data. Now the problem what happened is sensors is a basic group G, and the top of the G star we constructing. G star is nothing but a function on a G. Then we apply the Pointryagin duality transform measurement problem into mapping a measurement uncertainty dual computability. What happens is G star is open and then locally abelians, like open and abelian, then we have a that is proven that quantization duality G star has a isomorphic to G. That means there is a one census which is agree with all the things. Like we would have found so many values on the observable, but that will lead to the one reading. Like that's what sensor fusion all about it. Sensor fusion about getting one reading by from the observed data. That's what physically it means. But here we introduce one variable, one of the scale called Kolmogorov complexity. That is essentially to use to measure the level of input variable what we are getting. The the proposal, and of course we propose this quantum sensing can come back, and the sensor data analysis is crucial for various applications. We explore the concept of Kolmogorov complexity and entropy pointed duality. These three. The next slides will discuss with that. Entropy measures, and that we must suppose we agree. Calculate entropy using probability of sensor readings, dual space construction of the relation to entropy. This is what point of discussion process that we constructing dual space such that that stands on the is a function or observable on G, where the sensor data. Constructing the state space is nothing but it should have a topological group structure, and now we should be able to measure the Kolmogorov complexity and entropy on the line, and pointwise and duality analysis on G, computability of functions associated with the measurement, then sensor fusions and Turing machines, and challenges on application in the real world scenarios. These are the steps are explained very detailed in the paper, in a written paper. I will that can be referred if required. That Kolmogorov complexity measure the of course the shortest program to reconstruct the object. It's unlike a Shannon. Shannon doesn't talk about this. That's talk about information complexity. It doesn't talk about the source. But Kolmogorov talk about the source. So perhaps the physical process on the top of sensor, on the top of the observables. So for observables, only it's accessible to us. Sensor is some kind of a method and apparatus. Below the sensor, there is a physical reality. We want to measure them by using many sensors. After reading the many sensors in the form of observable, we want to take a one decision that's called sensor fusion actually. So there we want to estimate the Kolmogorov complexity via the dual group. So the when G star is a character, or is every element in G star is a character in G, is that means the G2 mapping to some complex circle is S1 or Z, which is there we want to know if the element, if G star we know, and then almost there it is it has a Kolmogorov complexity. We almost found it kind of things. That's that intuitiveness we use it for next result. Unveiling the complexity of the sensor data. Kolmogorov complexity measures the information content of the source actually, right? Intuitively, the shortest program reproduce the data. That means we know what was the source actually. Apply the Kolmogorov complexity to sensor data patterns. It can be as simple as like a database. Normally, this is used for PK zip and all the analysis. Israeli science used for that. Example here is estimating complexity of temperature fluctuations and so forth. Then what happens, we extend this one continuously. There's a Kolmogorov complexity measure the shortest program to generate the given data in the context of sensor networks. Now here in particular in the sensor network, Kolmogorov complexity can be applied to estimate complexity of sensor data patterns. There are so many patterns are emerging out of sensors. That complexity we can measure it actually. Constructing the state space. Now we want to construct the state space for sensors, and with the topological group structure on it, it is closed under group operations, allows for analyzing sensor data in a structured manner. That's the beauty here which we're trying to do it, so that things can go routine and rational. Otherwise, ad hoc methods, I told you, you told you, if then else, or we want to remove those if then else actually. Quantization duality is a mathematical concept that relates to the topological group. It's a dual space. providing insights into the analysis of sensor data. That's the thing which we are using it heavily onto this. And the Kolmogorov complexity side, utilizing Kolmogorov complexity and Pontryagin duality, we can compute functions associated with the sensor measurements. One such a function can be like a Fourier transform, or a discrete cosine transform, or a discrete sine transform, or Hilbert trans, whatever, or now some of the transforms, contributing to the understanding the sensor fusion and the information processing. Right. Once we know that, Fourier transform that, then we know which frequency signal is coming. Say the 400 hertz. Okay, this is fine. So there is a kind of physical reality is observed by human being out of that. The human connection, sorry, the connection between sensor fusion and the Turing machine problem opens up avenue for the exploring the limits of challenges of computability large-scale sensors. The moment we connect the sensor fusion and Turing machine problem, we are almost there with immediate further results onto that. The combined concept of Kolmogorov complexity, entropy, and Pontryagin duality is used into that for that to introduce a quantum sensing program for a robust data analysis. Of course, that is advanced sensor fusion and information extraction actually. In bottom line, we need to have a group structures, which is a time series data of n sensors. Each sensor has its time series data xi of t, and put them x1 to xn. Then we build a dual group G star. How do you build a dual group? Correlation between G star. G star consider continuous characters mapping from complex numbers. It's like x theta is a character. It's nothing e to the right theta t with range is uncle delta t, sorry, theta t. The G star element is t character function x theta 1 to x theta t is there like. So now G is n functions on the n sensors. On the top of that we put t functions, 1 2 t function. The t functions are setting elements in G star actually. Constructing the state space now. The state space is the one which is going to be more meaningful for us. Sensor data can be represents element in topological group G. It's below G star. Constructing the state space allows the structured analysis. Here we use the result from Pontryagin duality connects from G to G star via Peter-Weyl theorems. Leveraging Pontryagin duality for function computations. Associate function with the sensor measurements and mapping sensor data to dual space analysis inside the sensor fusion information. These steps are explained clearly as a paragraph and on derivations are given, but bottom line is the computing functions is an element in the Pontryagin dual space. See, that's what it means for us. It means element in G star. Now constructing G star is exercise. There is Python program or C code or something available to us now. That's which lot of work is going on. As the moment we know the observed data from sensors in sensors, then we need to apply Brooks-Engel algorithm to get rid of all faulty sensors. Then take this reasonably good sensors. Then we need to trust those sensors, their readings. From there, we'll construct a G star. That means every G star has observables, character maps, and then implication of this one, and then we can use that observables of sensor fusion actually. We should make sure the sensor network is a group of sensors. To do that, we need a G should be a topological group. Apart from we need to be able to define a metric onto that. A dual space of G star and its relation G, we need to be able to define Pontryagin duality isomorph. If we do these two, second and third, then fourth is good for a G isomorphic to G star star. That will give the essence of sensor network and group of sensor understanding, right? So a locally compact abelian group model the sensor networks. We use Pontryagin 1 Campen duality theorems, mapping function via the Peter-Weyl theorems, sensor fusion observation on the G. Only we have a fourth element item. In the first three we had to construct it actually. Sensor classification fusion play a major role in the sensor networks. MBA algorithms and Boltzmann machine operate powerful techniques. Pointage dual space provides insight into sensor fusions. Understanding these methods enhances sensor network applications. So then with this new element we introduce a Turing machines. What it's a sensor fusion resembles like a Turing machine problems. Turing machine process a symbols on a tape. In the sensor fusion, sensor data resembles a symbol screen. Sensor measurements are input to a computation stream. So yeah, so now we are almost clear about two sensor fusions. It's nothing but counting the Boltzmann machines, which was trained and then given the input, it can identify when reading frequency can go one. That's where substitution is happening one side. Another side, which we talked about, it is about the convergent duality, where the each element is a measurable function. That function is as a computable. If it's computable, what's the method in apparatus to devise such a function? That function can be programmed, like for example, like a Fourier transforms. It can be like much better than that. That Fourier that program can I given to Turing machine. The Turing machine take that program for the given input in the sensor and then produce observables. This is a setting. In this setting, which we define now, focus on creating quantum sensing program P that can exploit quantum superposition and entanglement to process the data from the good sensors in the group G. We encode the time series data from G into quantum states such as a qubits and quantum state. To do that, we suppose this already explained. I'll once again run through that. Left side is a Kolmogorov complexity. Right side, the Turing machine acts on the program P, produce the observable SI is a string. P is a minimal programs. Quantum sensing, what happened? We assuming that there are S n minus are observable we found. In that there is only one program P is there to give such a one. If such a P exists or not, first we have to find out. Then if there is a P exists, then if it is a computable or not, there will is a Pointage duality for computability. If there is a computable proven, then there is a method in apparatus to write the code. So this is a central problem in the whole sensor fusions. So three different problems. As a special case, one program P is providing a many with output S. As an inverse problem, it is a challenge to show the existence of P. The program P resulting in the string S1 to Sn minus or via Turing machine. In the normal case, the program P is expected to produce a one string S, but in the above case, one program P produces N minus R strings. That's a beautiful thing. And suppose 3 plus 2 equal to 5, that's what a normal computer we expect one program to give output. So fine. Instead of quantum, what we get is 5 when the 5 have a probability of 90%. On the 5 has a probability of 93%, 4 has a probability of 30%. We have so many outputs will come, right? That's we when programs gives us so many outputs, it can happen. That's what like a quantum sensing all about it. That's equivalent to our sensor network problem, fusion problem. So many data which we got, but we want to have only one data. Imagine room full of 100 of temperature sensors, but we want a room temperature only one. So we have to fuse them and get the correct one reading for that. So similarly, n minus r observation might lead to one quantum state. If you know the quantum state, then rest is quantum observed strings are associated with the group G. Finding such a program is equivalent to performing sensor fusion in G. This is what the intuitive thinking which we are thinking about. I hope is it's going to open up a new area of research, and that's a measure to obtain a multiple observables. The goal is to develop a quantum sensing program P with the multiple observables, utilize the quantum superposition and entanglement. And we are coming very close to, on this presentation, the quantum sensing program B. There are a few slides are there, which I'll leave it sure it is well as, given in detail in the paper. So I'll just move out that two slides. Then I'll just move to conclusions. In details, what happens is the Brooks-Wenger algorithm is a cooperative multi-agent algorithm proposed by Rodney Brooks and Professor S. Sitaram Iyengar. It enables a cooperative behavior in multi-agent systems with limited sensing and communication capabilities. If the readings are good, then we no need to worry about it. When readings are bad, then we have these issues. So we use a BA algorithm, this deterministic one, and stochastic. We have a Boltzmann machine is a stochastic recurrent neural network used for unsupervised learning. It employs energy-based learning and probabilistic modeling. The equivalence between deterministic Boltzmann machine at zero temperatures and the Brooks-Wenger algorithm recommends practical implications such as using an algorithm for a Boltzmann machine weight initialization. This is what I think this conveys strong evidence like in neural network. We W always we have random numbers. Random weight is a random. So it takes enough time to converge. It can converge the wrong place also local minimum. Imagine with the starting point itself like instead of Boltzmann machine t equal to non-zero, imagine Boltzmann machine at t is equal to 0, then become Brooks-Wenger algorithms. So that is solvable in a given times. Then that starting weight can be more meaningful weight than the randoms. If you have more meaningful weight, it's the potential of it converging to the global minima is very high with the less number of times computing. The connection between the measurement problem, dual space, and Pontryagin duality in sensor network requires a detailed research and understanding implication. But the early results, what we found out is says that Pontryagin duality plays a major role in sensor fusions by constructing the dual space of the given group structure, and the dual space has its own elements that is provides the computability of the sensors readings. That means that there is a well-defined Kolmogorov complexity for that. The moment the element is in a G star, we can almost say that no Kolmogorov complexities exist, but one doesn't know how to compute, right? So that's the way what we talk about it. From the observable, we find a program which produces those observables by using Turing machines. Then utilizing Kolmogorov complexity for the measurement problem and dual space computability has a theoretical implication needing the further research. Yes, that's the place I think there's a lot of gate is getting opened out there. Sensor fusion and quantum sensing and measurement, these are all interrelated appears to be, but it required a further careful additional research and innovation to connect them very tightly and climb some solid results onto that place. Actually, I'm almost done. If any questions, I like to take, and also thanks to organizers of World Innovations and Tech Expo 2023.
Thank you, Dr. Jayakumar. Thank you very much for your presentation.